Hi everyone. My name is Alice. I'm from Carnegie Mellon University. My supervisor is Dr. Bhattacharya. Today I'm here presenting my research work um, on testing the young FRB progenitor hypothesis, which is a cross-match of Catalog-1 CHIME bursts with historical local universe supernovae. I don't think I really need to introduce this a lot, but basically FRBs, fast radio versus intense bursts of radio waves of millisecond duration, and they were first reported in 2007. But the thing about it is its origin is still unknown, so that's what we're interested in finding out about its origin. And so we've had some observations. The first one was FRB-like emission detected from a known magnetar formed from a core collapse supernovae. And the second one is host galaxies where FRBs were formed are mostly star-forming galaxies. So core collapse supernovae, star-forming galaxies, and several FRB models have already suggested that young young and highly magnetized neutron stars can produce FRBs. By young, we mean it's less than 1,000 years old. So with these three observations, we basically formed our hypothesis of that young magnetars formed from core collapse supernovae are sources of FRBs. And our method of testing this hypothesis is cross-matching Catalog-1 CHIME FRBs with type 2 and type 1 core collapse historical supernovae. So we basically have two different data sets that we extract data from. The CHIME, I don't think I also need to really dig into the information about this, but it's basically a transient telescope that's very powerful for detecting FRBs. And we're using the Catalog-1 data from CHIME that has 474 non-repeating FRBs, so unique FRBs. And among these 474 FRBs, we have 128 of them have baseband localization, and then we have 2 of them have side lobes FRB localization, and then another 344 of them have header localization. So basically, baseband localization is more precise like count localization of such FRBs, and the header localization is we have different possible regions that the FRBs could lie in. So they're just ways we can locate the FRBs. And then the other catalog that we have is for the supernovae. So we have, we're using the Sternberg astronomical supernova catalog, and then there were originally 6,546 supernovae that were before and in 2014. And we included only type 2 and type 1 core collapse supernovae. So only the core collapse supernovae were left in the sample. And then there's also some other data sampling, data extraction that we needed to do. And here are the criteria that we did for these data sampling. So for the supernovae, we already only have type 2 and type 1 core collapse supernovae. And then we also kind of eliminated those ones that didn't have redshift in the catalog. And also they need to be visible to CHIME. So we also extracted those that were below negative 11 degrees for declinations. And then we also used another catalog, which is Hecate, to extract host galaxy properties. So Hecate has a constraint of 200 megaparsec, which is basically redshift of 0.043. So if any supernovae fall outside of that range, we also kind of eliminate that from our data sample. And then for FRB, we have repeater and non-repeaters. We only included the non-repeaters. And then the dispersion measure, we also only used excess dispersion measure that's less than 500 parsec centimeter negative cubed. And then there's 3 different localization methods that we used. So a quick run through of the process. Basically, this is the whole catalog, and then so this is the whole catalog, and then we have redshift and no redshift. We only included the type 2, and then they need to be visible to CHIME, and then also within the Hecate detectable region. Okay, and then for FRBs, we also use dispersion measure as kind of a constraint. So dispersion measure is quickly just quantifies how much a signal's arrival time at Earth is delayed by passing through a plasma. So with that, CHIME Catalog-1 provides DM excess in the form that it has contributions from host galaxy, intergalactic medium and Milky Way, and also circumgalactic medium. With these three contributions, they form the DM excess, and we did a 95% percentile, basically upper limit that we landed on 500 DM excess as the constraint. So we only include all the FRBs that's within this constraint. So yeah, now we have so we started with 600 and then we landed with 474 non-repeaters. And then with the DM cutoff, we had 241. And with these three, we have three different methods that we localize the FRBs. So baseband localization, which is a more precise method, and then the side lobes FRBs, we only have two, and they didn't have header localizations, and then 169 header localizations. So now we have all the database that we need to cross-match. So basically cross-match is we localize, so compare their different localization and see if there's any FRB and supernovae that's close within 2 arc second. So now this is a sky distribution map that I'm kind of showing all the data samples. So the triangles are the FRBs, and then the supernovae are the circled dots that are color coded by their exposure time. And all right, so after the cross match, we have 4 basically detections or pair of detections. And after we did some other analysis, only 1 pair was really plausible. And I'm going to jump into why only 1 pair is plausible. So basically, it's based on their host DM estimated using scattering timescale. So we basically used scattering time of these FRBs to figure out their DM excess. There is a relationship that I'm not showing. I should have put a equation that's on there to show why how we calculated the DM excess using the scattering time. But basically, they're proportional, and then after we estimated all the DM excess, only this FRB 2019-04-12B satisfies this inequality. So this is the only pair that we've found basically in cross-matching 886 supernovae with 241 FRBs. So here I'm showing the results. We found nothing using the baseband localization, which is a more precise method. And then these are also none from the 2 side lobes. These are the header localizations, the localization maps. You can see there are different regions that the FRBs could fall in. And the cyan circle dot is the supernova. So we're showing the 60%, 90%, 95% percentile of these regions. So basically, these dots fall within the 90% region. And you can all see that the excess DM is quite high for these 3. And then I'm showing the supernovae in their galactic image also. The little red square is the center of the galaxy, and then the plus sign is the location of the supernova relative to that galaxy. So we have 3 type 2s, and then this actual plausible detection is also type 2, but then you can see the excess DM is much lower than the other 3. So after calculating that, we decided this is the only plausible pair. All right. So now we moved on to calculating the chance association. So basically, is that actually possible? Was that how possible is it that we find a pair that's actually it? So we we just sampled 886, the same number as we had of the supernovae sample before. So 886 pseudo supernovae, namely just their RA and DEC positions um, that are in the CHIME sky coverage. And also we had them distributed uniformly. And then we used the same method. So we have header localization, baseband localization, side lobes localizations of these FRBs, and we cross-matched that with these FRBs. And then we found that the probability of finding greater than 4 incidences is 0.966. So basically 96.6%, which is quite high, but makes sense because we also used Poisson distribution to calculate this percentage, which is also 0.966. So that just kind of shows that maybe we couldn't really find any pair, but we also did further analysis. So this is an analysis on free optical depth constraint. What that is basically, so our hypothesis is saying that FRBs could be produced from these core collapse supernovae. These supernovae actually have ejecta that could significantly impact the observability of FRBs. So basically, the FRBs need to escape these ejecta to be able to hit Earth to let the CHIME detect them. And as the ejecta expands and thins, the FRBs become more observable. So we defined a free transparency timescale, which is basically the time till the free optical depth is equal to 1. So this is a parameter that's quantifying when FRBs are absorbed and cannot be escaped and cannot be seen and detected by us. So typically the type 1B and 1C is about 26 years, and then the type 2 is about 91 years. And none of, our sample of supernovae are not really that age. So they're only, the oldest one was from 1883 and also 19 something. So not also from the 4 pairs, they're all kind of young. Let's go back a little bit. So this is from 2019, and then some of them are like 2014, 2001, 2003. None of them are really falling into this 91 years and 26 years age or year age. So in the real life, the ejecta is not smooth. So they basically create low density paths. Basically, that's saying FRBs could still escape earlier because the ejecta is not smooth. There's like maybe thinner parts. So this analysis is basically suggesting that even though our FRBs or our supernovae are not old enough, but it is still possible that our detected pair should be detected. So that's just saying the pair should remain plausible. And we also did another analysis on burst rate estimation. We calculated the 1 sigma upper limit of burst rate estimation for these 886 supernovae. And then we basically placed hyperactive FRBs onto these positions of these supernovae. These hyperactive FRBs have a very high burst rate, so around 1 event per hour at max. So this part of analysis is just suggesting that if we place these hyperactive FRBs onto the positions of our samples, so these 886 supernovae, we should have detected those FRBs. So that's also suggesting that the FRBs are not hyperactive enough, or basically, are we actually seeing these pairs as the true detection, or is this hypothesis just not possible? And then we had kind of a continuation of our current work. So the motivation is that hyperactive FRBs also have radio counterparts. And if we can find, identify and report new discoveries of these radio counterparts from these supernovae, we can probably link that, oh, these supernovae might provide these or like produce these FRBs. So it's kind of like A is linked to B and B is linked to C, and can we link A to C kind of situation. So the database is still these CHIME visible core collapse supernovae that we had, 886. And then we cross-match those with the VLAS, using the VLAS survey, so Very Large Array Sky Survey, to detect these radio counterparts. We found 9 detections, and none of the 4 detections in our, so before in our FRB part of research were detected in this part of research. That's also just kind of showing that possible rejection of the hypothesis. This is a plot I'm showing the luminosity of the supernovae versus their time since explosion. So a hyperactive FRB typically have luminosity of 10 to the power of 29. But you can see most of these, or honestly, all of these supernovae are under that range. So most of these are around 10 to the power of 28 or below. So that's also suggesting that, oh, these supernovae don't really have energy that's pumping these hyperactive FRBs. So this is a kind of like a extra work we're doing to further prove or find evidence for our hypothesis. And for each source in this work, we will analyze their observed variability, evidence of persistent emission, supernova age, and relevance in comparison to expected radio supernova behavior. This is an example detection that I'm showing here. We have supernova 2004 decay. That's a type 1b. It's off-centered, so it's basically not in the center of the galaxy. And from the light curve, you can see that it's monotonic rising here. So it's a transient. Okay. And now we jump into the conclusion. So basically, we found 4 detections, and only 1 indicates a plausible association between the FRB and supernova. The PCC, the chance association probability, is really large. And based on the burst rate estimation, we found that if hyperactive FRBs are located at that site of supernova, CHIME should have detected it. And then we also did the free absorption analysis, suggesting that free absorption might be a factor for a high chance association, because FRBs need to really escape those ejecta to be able to detect it. So yeah, this future work is basically this VLAS, and we also might constrain our evolution of magnetar as FRB source activity with time. Okay, I think that's the end of my presentation, except for this extra slide is basically talking about that if we remove some of the DM constraint, we might find more detection pairs. All right, thank you, everyone.
Thank you.
And sorry about the loud noises.
No, it's all fine. Yeah, questions for Alice?
Hi, Alice. Sorry I missed this, but could you explain again how you measure DM excess? Because there's no host associations, right? for your FRBs?
Right here, about how the DM is estimated.
Yes.
Yeah, so
DM excess. Yep.
oh yeah, DM excess was not something that we physically estimated. It was provided by CHIME, so it was in that catalog. Here we're basically just talking about how uh different contributions were like combined to form DM excess. So just kind of like explaining the concept here. And what we did here was using these DM excess, we found a 95% percentile of the possible DM that's associated with supernovae. So the 95 percentile region, if I can use my mouse here. So right here, it just falls on that 500 parsec centimeter cube.
Oh, sorry. So these are DM excesses for the supernova host galaxies.
Yes, so the FRBs, I believe this was so I don't think I really explained it so well, but the DMX says yes, it was provided by CHIME. We didn't really estimate anything from the host. And
Okay, thank you.
yeah.
Any more questions, Resmi?
Hey, wouldn't it also be meaningful to include type 1A in the analysis, because we have at least some offsets which are consistent with type 1A?
Yeah, are you talking about so are you talking about we should also include type 1 core collapse supernovae in the sample? Yeah. We did include type 1A core collapse. So the sample of the supernovae were basically core collapse supernovae, and with the core collapse supernovae, we have type 2 and type 1 B1C. So the type 1 B1C were in the sample, but the detection pairs were just nothing involved that type 1. So here you can see like all of the detection or type 2. It's just because we have more like the percentage of type 2 supernovae in the sample were higher. Thank you.
Thanks, Alice, for joining us.
Yeah.